Hello everyone. In this video we're going to start chapter 2, atomic structure and interatomic bonding. Now we're going to review some of the chemistry things. We're not going to go deep into chemistry. We just want to know that how as engineer we use interatomic structure and interatomic bonding to understand the property of materials. Now I'm sure that in chemistry you all studied those things. We're going to review them, so it will be a short chapter. We're going to focus on the part that we need to know that are related to the properties of material. Now one may ask why we need to know about interatomic bonding. The atomic structure or the interatomic bonding, why we need to know about those information. Now you know that graphite and diamond are carbon. The parent material is carbon. So why carbon in a graphite behave in this manner? It's soft, greasy, while in diamond is hard, which is the strongest material. Now what does it makes this difference in carbon to behave as graphite and to behave as diamond? Now this is the way that the bonding or interatomic bonding or the atomic structure of the two of them, graphite and diamond, are different. Now if you understand the way that they bond, then we'll be able to understand the difference between each of them, and it will provide us information on the properties. So we will start reviewing some of the chemistry things that we already know them, but we have to just follow some of the things to remind you those information. Now when we're talking about atoms, basically we mean by nucleus plus electron. Now this is an atom we're talking about. Now nucleus basically made of proton and neutrons, and electrons, which is basically surrounding the nucleus. Charges that we have them, we know that electron and protons, they have negative and positive charges and the same magnitude, and neutrons, we know them are basically neutral. We know electrons are negative, protons are positive, and neutrons are electrically neutral. The charge, basically, they're called Columbus, 1.6 10 to the power minus 19 Columbus. This is the magnitude of the charge that they have it. Now, don't worry, those things we just need you to remind them. The mass, basically, and we know that proton and neutron have the same mass. The mass is very, very small, but however, it's bigger than the mass of electron. Now, electron basically approximately 2,000 times smaller than the mass of proton or neutron. 9 to 9.11 10 to the power minus 31. It's almost around 2,000 times smaller than the proton or neutron. That's why the mass of electron basically is neglected in the calculation of atomic mass. Now we have atomic mass A, which we're going to use it for the later purposes. So you already know mass of proton and mass of neutron is going to give us the atomic mass. We know that. And there is another thing that we needed, atomic number Z, which is the number of basically protons within the element that we have it. Now there is another term that we will understand, isotope, which is neutrons define the number of isotope. Now what does this mean? Before going further, I'm not sure in chemistry if you know that we have, for example, two types of carbon. We have carbon 12 and we have carbon 14. What does this mean? Carbon 12 means that you have 6 proton, 6 neutron inside it. So 6 proton and 6 neutron we have it there. We're gonna finish it. However, in the carbon 14 we have 6 proton 6 proton, but we have 8 neutron. We have 8 neutron. Now this is, we call them carbon isotope. Carbon isotope, two way that carbon forms or has. It's the way that in a nucleus part, which is proton and neutron, we have it, the number of neutrons are higher than the number of protons. Now this phenomenon is basically one of the good characteristics of material that as engineer we're using them for a lot of purposes. Now in the medicine, the MRI, when they use radioactive materials, and there's some wave that it comes out from this material which is totally harmless to our body, they're using it to scan or to basically follow the blood to an organ, or at least to see what's going on within our body. Now this is one of the material that will be used there that has some extra nucleus. Those nucleus basically is providing some extra waves they're giving it. Now I'm not going to talk about this, how does those neutron basically work. There is a video I can share with the student to understand the different way that those basically isotope, how it's going to be useful for peoples. Now this is going to change in different ways because it's unstable, so we want it to be stable. So what will happen to these 8? One of them will turn into proton, or will we make it electrons? So there is 3 different ways, or just going to go away, rearrange themselves to be stable. In this process something will happen. Those are something that for those students interested to see that how those will be useful. For example, uranium has this radioactive material. I mean, this is basically one of the isotope of uranium that has this property, giving this property to the material. So as we said, that understanding those things is going to give us idea how those materials are behaving in real lives. Now there is 2 things that in chemistry they're talking about: atomic mass and atomic weight. Atomic mass and atomic weight. Now the way that normally atomic weight, we normally using atomic weight in a calculation, but we have to know that where does this atomic weight came from. Now first we have to talk about atomic mass, which is AMU, atomic mass unit. This is, it says that for example you have a carbon which is 12 carbon. If you see 12, you're talking about carbon. It's basically, we say atomic mass of carbon, which is carbon 12, it's 12 AMU. Now this means that 1 AMU it's equal to the mass of proton or neutron. So 1 AMU, atomic mass unit, is equal to the mass of one proton or 1 neutron. So when we say carbon 12, where there's a 12, 6 proton, 6 neutron, so it will be 12 AMU. Now, however, due to the fact that each element, they have isotope, they are not just, it's not C12, carbon has C14. The others, they have a lot of isotopes. Some of, for example, iron has 4 or 5 isotope. Nickel around 6 isotopes. So each of them, they have different isotopes. If I'm not wrong, for nickel, I don't know if it's 6 or 5, but many material, many elements, most of them, rarely some of them, they don't have isotope, but mostly they have isotope. So due to that reason, another terms come into calculation we call atomic weight. Atomic weight of an element. Now atomic weight is basically, it's weighted average. It's average of the atomic masses. And we know atomic mass, for example, in the way that atomic mass in naturally occurring isotopes. So if naturally occurring, we have some isotopes, when we call them naturally occurring, what does it mean? That it's available in nature. Some of them synthetic, that's different. We're not going to go for synthetic one, which is man-made. Naturally occurring isotopes, in that way we will get atomic weight of carbon. Now atomic weight of carbon is 12.011 AMU. Still they're using this unit, atomic mass unit, but we call atomic weight. Look, the unit is still atomic mass unit, AMU, but because it came from the average of masses of the different isotope, then we call this one atomic weight. And normally we're using atomic weight in the calculation that we have it throughout this textbook, which as you can see it in chapter 3, chapter 4. We're going to use atomic weight of an element. You already know these things from chemistry. Now, there are some other things, that terms that we have to know. Mole, which is basically one of the main units that we're going to use them. A mole basically it's amount of matter, or it's like when we say 1 mole of carbon, it basically means that it has a 12 gram of carbons. Now where does this came from? Where this came from? We know that in this manner, one atomic mass unit is equal to 1 gram per mole. 1 gram per mole. This is the way that we're going to use them. Now, as we said that, since carbon has 12 atomic mass unit, so this will be 12 gram in 1 mole. What does this mean? It's gonna give us an idea that how many gram of carbon is equal to 1 mole. Because in chemistry we're gonna use mole. Sometimes for the solution, for the things that we say 1 mole of, for example, hydrogen has been used, or 1 mole of carbon, 1 mole, 2 mole of this one. So when they say 1 mole, it's basically, you know the atomic weight, so it's basically this atomic weight of carbon. It means that this much gram in 1 mole. So we're going to go for the atomic weight, this much gram in 1 mole. So if someone said 2 mole, that will be 24 gram of carbon. This is in chemistry we're using it, and throughout here as well we're going to use mole for the purpose of calculation. Now, another thing that we have is Avogadro number, which tells us that the number of atoms in 1 mole. Now remember, this is something I need you as engineer to know it. Look, for me, when I say that someone is engineer, I expect from them to use their brain for calculations. In chemistry, or at least for our material science, when we're dealing with those mole, atomic weight, Avogadro number, density, those things, when we're dealing with them, if you just use your brain as engineer, you'll be able to solve the things easily. Now, let me just make a simple calculation here. Now, we know that, for example, for carbon, since carbon datas are here, for example, 1 mole of carbon, we know that it's going to be 12 gram. Let's say it's going to be 12 gram. 12 gram. Now, inside 1 mole, we have, this is Avogadro number, we have 6 point, this is 22 for something going, but this textbook it's rounded to 23. It's 6.022, it goes 147 something, 10 to power 23 atoms. So it tells us that inside 1 mole, we have this amount of carbon atoms. Carbon atoms are small. 6 point, I cannot even read this number because it's 10 to the power 23. Don't know what will be the explanation where this is after. I only know after billion, trillion. After that, I don't know what will come. And the numberings, I'm never interested in that numbers after trillion. Now, in 1 mole we have that much atoms. We have. Now, what does it mean? Is this in a different way of thinking? If I have 12 gram of carbon, I know that inside those 12 gram of carbon I have that much atoms. Now, why this is important? Why? Because this 12 gram, it has a volume. Because each material, they have volume, yes, and we know it from even physics. Basically, we have density, we have volume, we have unit weight, some other terms that we have it. We'll explain for you. But if I just simply connect them together, someone is asking me, in 1 gram of atom, how much? In 1 gram of carbon, how many atoms do you expect? It's very simple. Why? Because we know that if is having this amount, 6.023, 10 to power 23, I simply can find it. 1 gram will be x. So we know this calculation, that simple way that I can find in 1 gram. This is in 12 gram, I know it. In 12 gram, in 1 gram, I can find it easily. So in chapter 4, or in chapter 3, sometimes when we're asking things, or mainly chapter 4, simply just by knowing the relation between those things, which I will explain in detail there, we'll be able to find information that we needed. Why? Because those information is going to provide us some other properties. Now, this is something I need you to understand, that so anything that someone is asking you, for example, in half mole, how much we have it, or half mole, how many grams, will be 6 grams, for example, of carbon, because we know the atomic weight. This is the way that we represent atomic weight unit. For example, iron, the atomic weight of iron is 55.85 gram per mole. What does it mean? I need you to understand the unit. 1 mole of iron is weight 55.85 gram. So if someone asks you, for example, 100 gram of iron, how many mole it will be, you will say that 55.85 is 1 mole, so 100 gram will be x mole. I can find mole. Easily, by just understanding the units, we can answer a lot of questions. Why? Because when it comes to chapter 4 again, we will teach you alloys. How do we mix things? So the amount of mixing, for example, it depends on those things that we have it here. We have those gram, mole, density, atomic weight. We can use those in order to our calculation. Now, there are some simple calculations. I'm not going to go through them, but ones can go, for example, they're asking the number of atoms per centimeter cube. You want to go for centimeter cube, you have to bring density. Why? Because the density has a unit which is gram per centimeter cube. Now look at here, what does this mean? Gram per centimeter cube. That means that, let's say this is carbon, yes, for graphite. Carbon for graphite. 1 centimeter cube of carbon, it's 2.3 gram. Or you can read it in different way. You can say 2.3 gram of carbon. The volume of 2.3 gram of carbon is 1 centimeter cube. Look, it's 1 centimeter cube. 2.3 gram of carbon. Basically, it's going to be 1 centimeter cube. I don't know if you can feel 1 centimeter cube. Your finger, if you take 1 centimeter, as a cube, 1 centimeter dimension. Look, 1 centimeter. Imagine 1 centimeter cube with 1 centimeter dimension. That's weight 2.3 gram. This is graphite. Now, like if simply I ask you, what about 1 mole? 1 mole. What is the volume of 1 mole? The volume of 1 mole, how much it is, the volume of it? Simply, yes, because I know that I can turn this mole to 12 gram, and from the 12 gram I can find the volume. Why? Because I said this is equal to 1 centimeter, then 12 gram is going to be, we're going to find the volume there. Or I can find number of atom inside here, because I told you that, yes, if I want to find number of atom inside here, I know that in 12 gram we have Avogadro number, then in 2.3 gram I can simply find the number of atom inside 2.3 gram, or inside 1 centimeter cube. People may ask you, for example, find number of atom in 1 centimeter cube. Well, we know that the relation that we have it between a number of atom is related to the mole, and mole basically related to gram. I know that 12 gram of carbon has Avogadro number, which is 6. We did this one, yes? We know that in 12 gram of carbon we have this much atom. Then, if I know the density of the material, I know that 1 centimeter cube will be how many grams. Then I can use this gram here, and I can find the number of atom inside that gram. This is simple calculation. You can just read them to understand what do they means. We're not going to ask those things basically, but it's good to know those information there. Now we're going to talk about electrons in atom. The way that they are basically surrounding the nucleus, and the shells. We're going to talk about the orbits that we have, and we're going to go for electron configuration. We're going to focus on those electron configuration in a bit, or in a different video. Now, I mean, back in, when was it, when I was in high school? I mean 20 years ago, like, basically, when the teacher was explaining to us in high school the chemistry, we were expecting that those electrons basically were following an orbit, that the way that the Earth is following Sun, basically in a different levels. Now, the teacher was explaining to us like this, but in reality, it's not something like this. They are not just following a path. I mean, even they cannot predict exact the location of this electron around this nucleus. It's basically can go like this. I mean, they following this, but the electrons here, they're following this nucleus, and they create a cloud. They call the clouds around the nucleus. I mean, they basically, the way that they call the cloud, they will produce a cloud. Even those, they will create a cloud. Basically, they have a place that, or an radius, or an area that they're following. They're not gonna come inside here. That's why they call them orbits, because of due to energy that they have it. We're gonna talk about those later. So, I mean, they were telling us that they I mean, mini system, but it's not going to be exactly in the same location. So the way that the electrons are following those neutrons, basically they create a cloud around the nucleus. I mean, the radius is something very small, according to the way that the number of atoms in the orbits that we have it. Now, how do we use those? I mean, in chemistry, you've heard about these orbits. I don't know if they use the principle of quantum numbers. They call them shell. Now, let's say, for example, this is a shell 1, this is shell 2, or they call them quantum number 1, quantum number 2. On the level 1, level 2, level 3. I mean, some they use a different way. I mean, there's a table, I think I can describe this on your heads better to explain them. Now, this is, or they call them principal quantum number 1, which means the first. I mean, imagine this is the nucleus, the first, I mean, the first circle, the atom, the cloud that atom is orbiting inside it, they call them quantum number 1, principal quantum number 1, or some they call K shell. This is a shell. The second one, basically, which goes somewhere bigger than this one, or it's supposed to be something circle or whatever it is, then that's going to be quantum number 2, or they called L shell, so KLMN shell, or we just simply follow the number, so we call it 1. We're going to use even 1 for our things. We're not going to say use K, it's easier for us. We're going to use 2, basically, which we describe the second one, and when we describe in the third one, basically we're going to go for 3, so this is going to be 3. Look, I'm going to explain why we have 3 times 3, or why we have 4 fours here. Now those we call them principal, or we call them shell. Look, shell, that means the big one we call it, or the levels, the quantum principle, the principal quantum numbers, we call this one shell. Now within each shell we have subshells. Now this is, we're going to use them for our electron configurations. Now inside K shell we only have one subshell, we called S orbit. Inside L shell we have 2 of them, S and P. Inside the third level, which is M shell, we have 3. That's why 3 times repeating, which is SPD. Those are each of them their orbit, and they contain electron inside them. For the fourth, we have SPDF, which is N shell. Now, what does number of state means here? Number of state. If you, let me just go for an empty space to explain this one. Now, if this is, for example, 1, S is S. S basically has one box. For the level 2, when we have it, we have S and P. P basically has one box, and S has one box, P has three boxes. The way that in chemistry you've seen this one, the electrons basically come inside here, and filling this box. Goes for D basically will be 5, and for F we have 7. So if you go, for example, if you draw D, basically you're gonna draw 5 boxes there, 5 boxes for D. This we call them states inside them. This is 2, 3, and 4, 5. Now what does this gonna help us? Those basically the states, number of states here. Each state basically contain 2 electrons. As we know it from chemistry, that basically inside here we have two electrons, and we providing in this shape, providing in this way. For example, here 2. Inside here we have 3 boxes, so expecting to have 6 electron inside p orbit. In d orbit we're expecting to have 10, because we have 5 times 2, we have 10. We're not going to use this electron configuration here. We're not going to use this boxing in order to do the electron configuration, but still we're going to use sp, but in a simple manner to do the electron configuration. So this will tell us that now per shell. Look, shell basically means that because each shell they may have subshells, yes. So in K shell we have 2 electrons. In the L shell we have L electron. Now in high school I remember these numbers: 2, 8, 18, 32. 2, 8, 18, 32. Why? Because in the second shell, which we have it, second shell, which is the L shell, we have S and P, 2 subshells inside it. In S we have 2 electrons, in P we have 6 electrons, so total number of electrons will be 8. And if you remember in the old version of doing this one, we will do it in this manner. If you were drawing, for example, this is the nuclei, and for example in the first shell we're going to put 2 electrons there, and in the second one we're going to put 8 electrons there, and we're going to put them in a pair. This was when we're using them basically in a way that 1 electron here, 1 electron here. When it comes here, we're going to put in a 2 in a pair, for example 2, 4, 6, 8. This was the way that we were going to do electron basically configuration at that time. Now we're going to use different manner because of the energy and all the surrounding the nucleus. We have it here. So this is the first shell, we have 2 electrons. The second shell we have 8 electrons, but we know that inside here we only have s orbit, and inside here we have s and p. That's why we're going to have 8, because s contain 2 electrons, p contain 6 electrons. Total number of electrons inside the shell will be 8 electrons, and then so on for the other one, 18 and 32 for 4 shells. We have some other 5, 6. It's going to continue the same manner as PDF. So those we're going to use them, those principles we're going to use them to do the electron configuration, and we're going to get some properties from those electron configuration that we have it here. Okay, before I'm going to use the next video, not to be long, to explain the electron configuration, and we're talking about the energy, the way that they're, which one comes before what. We're talking about the energy, and we're talking about why the energy matters here in order to understand why which one comes before which of them. So in the next video we're going to explain this one and some electron configuration there. Thanks for watching.